Okay, let's start the session then. So today we'll be discussing questions based on week 11 lectures. I'll share my slides. I hope you can see the screen.
Yes, sir.
Yeah, okay. So the last week's lectures were based on dimensionality reduction and sparse representation. So most of these, topics are generally a part of a statistical course, especially the dimensionality reduction part. But since it has a lot of application in computer vision, so it was done in this part. Okay, so we'll start with the first question then. uh, so before we start, what do you mean by dimensionality reduction? Any answers? What does it even mean before we start off with the question?
Representing the data in lower dimensions with all the with same variance and mean.
um, Not really the same variance always, but yeah, we would like to represent the data in the lower dimension because we believe that things are placed in a lower dimension subspace. It's just that we have represented it in a higher dimension space. For instance, if you have a plane area, if you have just a plane in this 3D world, that means it just needs two coordinates to be represented. But since we have placed it in the 3D world, we might we might represent each point on the plane with three elements, right? But actually it's just lying in a 2D space. So I mean that's a typical example that people would give you, that it would we would like to reduce the dimension to such an extent that that dimension fits the whole data. But sometimes it's also possible that you have noise, for instance. So you might have a set of points out there, but you know that those set of points belong to a plane. But the problem is, because of noise, uh, if you see the elements of those points, you can clearly see that it covers the whole 3D space. But that's not actually the case. It's because of the noise that it's covering the whole 3D space. If you just try to fit a plane based on those set of points, then what does it give? It's kind of denoising the whole plane. You can think of it like that. And it's actually used for denoising purposes as well in image processing. So yeah, one of the most commonly used method is principal component analysis, and we would start off with that question. So which of the following are true regarding principal component analysis? It finds a minimum dimensional subspace for representing the data. What do you think? Is the first one right? So principal
Yes, sir.
component
We go with
analysis, yeah, yeah. Principal component analysis is a part of uh, dimensional reduction method. So of course it tries to find the minimal dimensional subspace for representing the data. So that's true. Okay. So this is right. The next one is the dominant component corresponds to the one with maximum variance for a given set of data points. What do you think? So okay, let's take an example before we go ahead. So, so if I have these purple dots as a set of points given to me, and the screen is a two-dimensional space. So I would like to find the dominant component out here. So first we'll try to understand what do you mean by dominant component. So let me uh, try to take different projections. For instance, if I take Okay, let me continue with this. Yeah. So if I take some direction like this, and if I try to project points on this direction, so you can see that in this specific direction only this much of the data is captured. The rest of the data will not be captured. If I try to take this specific direction, you can just see that this much of the data has been captured. But if you try to take this direction, this specific direction, and if you try to extend it this way, you can see that this amount of data has been captured. So what do you mean by taking a direction and continuing with it? So I'm just trying to project these points onto this direction, orthogonal projection. So how do you do orthogonal projection? It's pretty straightforward, right? If I have this point P and if I have this direction V, so this point P is what? This point P is some vector from the origin O, right? So so if V is unit vector, then I guess the projection onto the direction V is what? So let us keep it as small p. So it should be P transpose V, right? So this is the projection onto the direction V. So given these things, so we would like to maximize this projection P transpose V such that this V, I mean, we would like to find the direction V such that this P transpose V is maximized for all the points together. So that's the aim out here. So what do you think about this? The dominant component corresponds to the one with maximum variance for a given set of data points. So intuitively speaking, here you can see that the spread is more in this direction, the spread is less in this specific direction, and in this direction the spread is the least if you take the one dimensional vector v. So this is the maximum, uh, this is the component which captures the maximum variance of the data. So we would like to take this component. So the dominant component is this, and yeah, this statement is true. The dominant component corresponds to the one with maximum variance. Because maximum variance, why? Because we would like to maximize this projection P transpose V. I hope this point is clear.
Yes, sir.
Yeah, okay. So the next one is it is an unsupervised method. What do you have to say about this?
True.
Why?
Because there is no labels that is required to
Yeah, there
like
is no
compress.
supervision label out there, so it's unsupervised. So we have to, given a set of data, we just need to find a specific direction in which this P transpose V is maximized. Okay, so it maximizes the expected magnitude of the dominant component. Is it right?
So we are only maximize like we are only keeping variance as maximum, right?
Yeah. So the aim here is to find the dominant component itself and not really maximizing the expected magnitude. So finding the dominant component itself is the aim, and so this turns out to be the wrong answer. So if you remember in the class, it was discussed that these maximum component, or rather all the different principal components, can be found out by finding some equation like this, where C is the covariance matrix. So this W are the principal directions, rather. I would keep it that way. Principal directions. And the lambda determines whether it's the dominant one or the other way around. Well, for this specific example, since we are in two-dimension space, so lambda will can only take two values, and there will only be two principal directions corresponding to the two lambdas. So this is covariance of data. I hope this part is clear. Any doubts?
No, sir.
Okay, we'll move on to the next one. Okay, so here we have to use principal component analysis. So this is question 2 for us. Consider the following representation of the data. So data is given in get data is given as rows in this specific question, and then compute the unit vector along the direction of principal component of x. So what do you need to do? Simple, right? We somehow need to first find the covariance matrix, and then based on that we'll just need to solve this eigenvalue equation to get the principal components. Okay, so okay, let's start. So we have this data given as row vectors. So what is the mean of this data? So mean is nothing but just you add the elements of the rows and then divided by 4 for this specific case. Okay, so what do we have? We are finding the mean reduced data. This gives us the mean reduced data. So what did we do here? We just reduce the mean. What's the next step? We need to find the covariance matrix, right?
Yes, sir.
Yeah. So this is wrong. So I'll just change the notation. Yeah. So how does covariance matrix look like? So covariance matrix C looks like this, right? X minus x bar. With this given notation, it will be transpose x minus x bar. This is nothing but summation over I xi minus x bar into xi minus x bar transpose. Well, there should be a 1 by n out here. Well, covariance needs 1 by n out there, but for our case, we just need this matrix. It's just x hat transpose x hat. So if you try to just compute this, it turns out to be something like this. And now once you have this specific matrix, you just need to find the eigenvalues. How do we find the eigenvalues? So let me call this as y, or maybe some other matrix a minus lambda I determinant should be 0 for eigenvalues. So it's like 10 minus lambda square minus 6 square, right? So 10 minus lambda is plus minus 6. So lambda should be 10 minus plus 6, which is 16 or 4. Hope this is clear. This is just straightforward computation. Based on
Yes, sir.
this, based on this, we just need to again place the values out there. So it's like 10 minus lambda 10 minus lambda times x1 x2 is 0. So this is what we need to solve for eigenvectors. So for lambda equals to 16, it turns out to be something like this. So this gives us what? X1 equals to x2. So our eigenvector, rather let me put it as lambda 1. So eigenvector v1 corresponding to lambda 1 should be what? Both should be same, but then they need to be normalized. So ultimately it looks something like this. Okay, so for the next lambda, how does it look? So it's like 10 minus 4, right? Okay, yeah, 6 6 6 6, which which, which gives us x1 is minus x2. So our corresponding eigenvector will look something like this. So this is the dominant principal component, and this is what? This is the non-dominant. Well, here there are only two components, so of course this is the non-dominant one. Okay, so of course the computations are pretty simple given that we know how to compute eigenvalues and eigenvectors. But do you understand why do we want to remove this mean at the first place? Any
We
intuition?
are centralizing, like
Uh,
bringing it to center.
okay, centralizing is fine, but why centralize? The data is ultimately in two dimensions. We just, I mean, for instance, if we have three-dimensional data and the actual data is in two dimensions, why do you want to centralize it to zero? Mm, okay, I just try to give some intuition about it. Of course, the maths proves it, but if we don't have an intuition, it's not pretty much useful. So suppose we have some data in these three dimensions x, y, and z, but this data is a planar data, for instance. So points on this plane is the given data to us. I mean, this plane extends up to infinity. I just had to give some feeling about plane. I'm giving it. I'm just trying to write a part of it. Okay. So given this uh, data, you know that it lies on a plane, right? So if you directly try to take the principal components of this, then what would it be? So if you see here properly, you will have this component added to each of the principal components, right? This component, and then there are of course other principal directions based on the data, probably one in this direction and the other in this direction. So this specific component is redundant. Yeah. So so we are unnecessarily adding this specific component because we want to represent the data in a lower dimension space. So what if we just reduce this component to zero? So then the whole plane will lie here, and we won't have any component like this, right? So for instance, if this plane is going very far away from the origin, then this is an unnecessary dominant component which is not required for our case because we know that the whole data lies on a plane. So we just want to remove such unnecessary components out there. So we just shift the whole plane to the origin. Once we shift the whole plane to the origin, We can then find the principal components on the plane itself. I hope the intuition is clear.
Yes, sir.
Okay, great. So we move on to the next question.
Sir, in that we might even be reducing one dimension, or we are not.
Yeah, the whole idea is to reduce the dimension, right?
Yes,
PCS
sir.
whole
No, sir.
idea
In
is.
like in the redundant information.
Uh, I did not get you. We are reducing the dimension meaning.
Like we saw the like we are centralizing it, right, sir?
Yeah, we are just shifting the shifting this plane to the origin. Yes.
So we might even be reducing one dimension or not.
No, I mean, why do
Okay.
you say that? See this. If this plane passes through 1 comma 1 1 comma 1, I mean 1 comma 1 comma 1 here, or rather, given this specific case, if I say that this plane passes here as 1 comma 0 comma 0 0 comma 1 comma 0, and this 0 comma 0 comma 1, it will just change the values out here, right?
Well, oh, okay, sir.
So we are just trying
So
to remove.
redundant means like we instead of adding all the like the numbers to all the points, we are
Yes, yes,
reducing
yes.
that.
Yeah, yeah, yeah. So this
Okay.
specific vector is common to all the points out there, right? If you once you reach on
Yes,
the
sir.
plane, then you can use the principal components to go out there and get the specific point. But this whole
Yes.
what do you say, shift from origin is creating a nuisance because we are not really able to analyze the data properly. Well, in this three dimensions, you
Okay.
can
Okay,
clearly
sir.
see it as a plane, but if you are in a higher dimension space, given a set of points, how would you know whether it's a hyperplane or it's just or some complicated data? So it's not possible, right? So it's always good to remove the mean out there.
Okay, sir. And there you like we selected the dominant component, right?
uh, yeah, I mean, at this point
So that is
we
based
will,
on the eigenvalue.
yeah, for this specific case we'll select the highest two dominant components to represent the whole plane. That's all.
No, sir. How did we select the highest dominant, like
So here in
the
this case,
first one?
since we have the data in three dimensions, right? So we'll have three
Yes, sir.
lambda values. If you have three lambda values, you just select the top two lambda values. That's all.
Okay.
So if these points fit on a plane exactly, then the third lambda will be 0. And if the points don't fit on a plane exactly, maybe there is some noise, then the third lambda will be very small, but it won't be exact. It won't exactly be 0. So there you can just
Oh,
choose the first two components, and ignoring the third component means that you are just trying to uh, denoise the points and fit a plane. That's all.
okay, sir.
Yeah. Okay. So okay, the next question is to compute the eigenvalues. Anyways, we computed that, so we can skip this part. Okay, so for the data given in question, to compute the total variance of the data points. What is the total variance?
Sum of diagonal elements of the covariance matrix.
Okay, yeah, sum of diagonal elements. Sum of elements is the total covariance, total variance, which is nothing but sigma 1 square plus sigma 2 square. That's all, right? So in this specific case, we know that our matrix is this, right? Sum of diagonal elements, which turns out to be 10 plus 10, which is 20. So this is our answer. The sum of diagonal elements also, you can say it as trace of our matrix which was formed, x hat transpose x hat. That's all. Okay, I guess this was pretty simple one. So I guess the next one is also relatively simple. So we have some data points given to us, five data points out there, and we need to compute the covariance matrix of this. Okay. Um, so we'll try to change the notation a bit out here. We'll represent the whole data. I mean, we'll represent each column as a data point rather than each row in the previous section. Okay. Now, how to compute covariance? We need to get the mean, right?
Yes, sir. Mean and subtracting.
Yeah. So our mean will look something like this, and then what to do? We'll find some matrix x tilde as x minus x bar. Okay, which turns out to be some matrix like this. I'll just write it out. Oh, yeah, hopefully the computations are fine. And then covariance is what we just derived the. So it should be 1 by n x tilde transpose. So here we have how many data points? Five data points. Our n is 5. Yeah. And then just take the product of this, which will give us some final answer like this. Okay. Yeah. Okay. Any doubts?
No, sir.
Any property of covariance matrix that you know?
So, upper triangular or lower triangle, like symmetric matrix.
It should be symmetric. Yeah,
Yes, sir.
it's a symmetric matrix. Yeah, because the way it's constructed itself gives us a symmetric matrix. Okay. Uh, Anything else? Where do you remember where did we use covariance matrix? Somewhere in distances, I guess. There are a few lectures back, not quite recent. Do you Can you just tell me where could covariance matrix be useful if you have to measure distances? Uh, no answers. Okay. So, do you people remember about Mahalanobis distance? Well, you can just check it out. So, our usual Euclidean distance is What is our usual Euclidean distance? Is some x transpose x, right?
Yes, sir.
So here it will be x transpose sigma inverse x. How will this help us? Can you tell that? How will this help us? So if I give you some data like, okay, my handwriting should just use this. Given this, maybe yeah. What do you see on your screens? It's an
Oval.
oh, okay. It's an ellipse.
Yes. Ellipse.
Yeah, I mean it's oval. It's fine, but it's ellipse for our purpose. Okay. So given that this is an ellipse, what does this do? If you have points on an ellipse, Euclidean distance measures what? So it will just it just sums up the components and squares of the components and sums it, right? So Euclidean distance will be something like this. For a point x, Euclidean distance will measure something like this, right? This is Euclidean distance. Okay, this is fine, but do you think it's a good measure? Yes, no, something? Now, if I say, okay, let this point be P rather. If this point is P and it has components x comma y, which one do you think is nearby, x or y? It looks like a square, of course, so you might say that x equals to y in this space, right?
Yes, sir. X equals to y.
Yeah, I mean approximately. Yeah, it looks similar, but the point here is we have our data spread in an elliptical fashion. So intuitively, what do you? I mean, this is if this is the maximum extent till where the x can go. It has not even covered half of it, right? But if this is the maximum extent the y can go, you know that it has almost covered the whole maximum possible range. Yes. Do you agree with that?
Yes, sir. Covered.
Yeah. So the point here is if you want to make these, uh, if you want to make it independent of what shape the data is, so you can, so you want to convert it into a circle. So if you convert it into a circle, this point will shift somewhere here. So this P is, yeah, this P dash will look something like this. P dash will have x dash y dash. So this is after performing the sigma inverse operation. So how do you get this? You can think of it like P dash is sigma half into sigma minus half into P. Yeah. Okay. Well, this is possible because it's a positive semi-definite matrix. So you can take if it's positive definite, then you can take an inverse, not for positive semi-definite, and then you can just reduce that. You can find a factor such that sigma half into sigma half is sigma. So this is possible. This transformation is possible. So given this transformation, you have tried to shift this point P to point P dash, and now you can clearly see that in this new space, in this new space, what x dash is closer to origin and y dash is far away from origin, right? Yes.
Yes, sir.
Yeah. So here we are mapping the same point from this normal Euclidean space to some other space, which we generally call as Mahalanobis space. I mean, it's not quite widely used that way, but we are measuring distances in this space when you consider this x transpose sigma inverse x. So where sigma inverse is the covariance inverse. That's all. Okay, so this is also called as whitening transform, and it's widely used in machine learning and other data analytics courses. Okay, so let us move to the next question. So we have data points given like this. Again, we need to perform PCA. Okay, there's too much computation out there, but okay, let's try this. And then compute the projected data points with redundant dimension. Okay, now let's try doing that. So this should be, so we'll first build the matrix out there. Next, what do we need to do? Take the
Mean
mean across which dimension?
432
Consider,
mean and 124 mean and 283.
yeah, so it will be a mean will be across this dimension, right? Because each
Yes,
of
sir.
these now represents a
Same
data
data
point.
point.
Yeah, same data point.
Yes.
So this mean turns out to be like this. Hopefully the computations are right. Okay. So what do we do next? We construct the covariance matrix.
X minus X bar.
Yeah. Yeah. Of course. X minus x bar. X minus x bar transpose. So this is the covariance matrix, right? Agreed.
Yes, sir.
So
Yes,
once
sir.
we have this matrix, what do we need to do? I mean, I'm not computing the matrix now. We have performed PCA by getting the eigenvalues. I mean, so let E contain the eigenvalues, right? E contain the eigenvalues of what? Of C. So once we have, oh, I mean, these are eigenvectors. Sorry. So E contains the eigenvectors of C, and we have stacked it as columns. And once we have this, what do we need to do? We need to project the data points with redundant dimension. So what do you mean by projection of data point?
The point transpose the eigenvectors.
Yeah. So the point transpose the eigenvector. So if I take a point xi, what do I need to do? First, I'll remove the mean. Yes. So this is a column vector, right?
Yes.
So this is a column
Yes,
vector
sir.
transpose the eigenvectors E. So this gives us projection on what? So what is this? This is a 1 cross 3 vector, and this is a 3 cross 3
3 cross 3.
matrix. So this gives us some 1 cross 3 vector, right?
Yes, sir. Yes, sir.
So each of these components represents what?
Reduced dimension of the data point.
No, we just projected the current data onto the new basis. New basis given by the principal components, right? Eigenvectors are the principal components here. That's what we did. Agreed?
Oh, yes, sir.
So what did we do here? We just, this is just projection of data onto the principal components. So which is the basis? Why is it a basis? Because these E will always be linearly independent, and of course they are orthogonal in this case because we have symmetric matrix out there. So for symmetric matrix, we have orthogonal eigenvectors, and so we have this new basis out there, which are the principal components. And what does the question demand? The question demands us to put the projected data points with redundant dimension. So once we have this projection out there, so what is the redundant dimension? For instance, if you have placed E1, E2, E3 such that these correspond to lambda 1, lambda 2, and lambda 3, the redundant dimension is what? The least
Lambda 3.
lambda 3. Yeah. So you will consider only this specific component out there. But here you need to find it for all the whole data. That means third component for all the three xi's out there. Each of these are xi's. So do you get the point out here? What are we trying to do?
We are just projecting the points to the principal components. That's
Principal
all right,
components.
sir.
Yeah. So initially we found out the principal components, and then since the question asked us to project the data with redundant dimension, so we will try to project it on the dimension which contains least information, that is the least eigenvector component.
We can extract the original points using this representation, or
You can extract what?
like after projecting, can we use that points to extract the real data? Or,
Yeah, of course. So what are the things that you need to extract the original
okay,
data?
eigenvectors,
Eigenvectors and
eigenvalues.
okay. Eigenvalues is not required to extract the original data, but fine. Anything else? Which is, what are the operations that we did?
No, we took mean
Yeah, we
and
took the mean,
subtract.
we subtracted the mean, and then we considered the eigenvectors of the covariance. So you need both the mean and eigenvectors of the covariance matrix to get back to
Okay,
the original
we
data.
do the reverse operation.
Yeah.
Okay, so
You think is it enough? No. Do you think is
is
it
there
enough?
enough in
It's not right. It's wrong. Um, yeah. Actually, it's fine. Since you have projected it onto this new basis vector E, you can do an inverse projection by taking the inverse of the matrix. Once you take inverse of the matrix, whatever data you get, you add the mean x bar, and then you get the original point. Okay, yeah. So the only thing that you need is the eigenvectors and the mean. That's all. Okay. So we move on to the next question. Okay, yeah. So here is something that we did, not exactly the same thing, but we did something similar in our first session. Do you remember what was that? We used some within class
Within class,
and between
yes,
class
sir. Within
variance.
class variance, yes, sir.
So what did we do in the first lecture? Where was it used? Rather, first session, not the first lecture. So it was used for Otsu thresholding, right?
Yes, sir. What's the
Otsu
thresholding?
thresholding for binarization of images.
Yes, sir.
So there we had two different cost functions, that within class variance and between class variance. So what did we want to do? We want to reduce the within class variance, which was same as that of increasing the between class variance. Yes, there we did it with
Yes, sir.
only, yeah. So there we did it with only one dimensional data, and this is something which is related to Fisher linear discriminant, where we are doing it multiple dimensions, not just one dimension data. So the same exact thing can be extended here for multiple dimensions, and that's what was done for the Fisher linear discriminant. Yeah. So what's the difference between Fisher linear discriminant and PCA? Where do you want to use which one? Any idea? I guess this was discussed in the lecture. I think so, yeah. So for PCA, what kind of data you have? Input data? You just have data points, right? Anything else you have given with for PCA?
No, sir. Only data points.
Yeah. But what about uh, Fisher linear discriminant? Or they call it as linear discriminant analysis as well in these lectures. So apart from data, what data points? What do we have? We have the class labels as well, right? So that's the best distinguishing factor between where do you want to use what. So if you just have some data and you want to analyze how that data is, you use PCA. But if you have data and then the respective class labels as well, class labels, uh, yeah, then what do you want to do? So you want to find how well these classes are separated, right? Instead of ignoring the classes and then
Yes, sir.
directly considering which the data as a whole. So since you have some labels, you want to use that information. So I'm just using the example given in the class, and I hope you people remember it. So you have two sets of data points. This these left ones belong to one of the classes, and the other right ones belong to the right other classes. So we would like to find how well are they separated. So that means we so if you do some TCA sort of thing on this, so this direction is obtained by PCA. This is some principal component V1, for instance. So if you try to project the data on this principal component, of course PCA is doing its own job. It's trying to give me the direction in which the variance is maximum, right? But here we are interested. in something else. Our aim is to find the best direction which separates these two data and also reduces the dimension. Do you understand? So
Yes, sir.
since our aim is changed now, so maybe we would like to have some other some other direction like this. So probably this one would be given by the linear discriminant analysis, or the Fisher linear discriminant specifically speaking. And if we try to project data onto this specific dimension, we clearly see that there is a huge separation out there. See, but here the data is mixed, as you can clearly see. So our aim here is different. If you have class labels as well, we would like to find the direction which would reduce these. We would like to find a direction which reduces the dimension but keeps the classes well separated. That's all. So that's how this is motivated. So the main components of Fisher linear discriminant is what? Well, it's given in the question. It's computing this within class variance and between class variance, or the scatter matrices here. Yeah, let's stick to the convention. So Fisher linear discriminant is something like this. We have SB as between class uh, scatter. And when can you use this kind of analysis, discriminant analysis? There are two important points out there without which our whole, I mean, points means there are two important assumptions out there without which the whole analysis can break down. What is this? Any idea? Since we are considering between class and within class scatters, think it should be intuitive here from here. So the whole aim is, I mean, the whole assumption out here is the points of a class are nearby, of a given class are nearby, which means that the within class scatter should be
Well separated.
yeah. So first we are talking about within class thing. So so the within class scatter should be low, right? Because within a class all the points are nearby. Do you agree? At least from this example.
Yes, sir.
Yeah, but now we go to the between class scatter. So these two classes should be well separated. So which is characterized by between class scatter. If they are not well separated, this analysis may not be that useful in our case. So given these two assumptions, we define these scatter matrices, and based on those scatter matrices, we can find our best direction in which this can be, in which the dimension can be reduced, as well as our classes are well separated. Okay, so now since we are clear of the aim, uh, we can just directly use the formulas. So what is between class scatter? This formula should be simple to remember. See, it is between class, right? So we are just trying to get an idea of how far the means are from each other.
Oh, yes, sir.
Yeah. So between class we want to maximize between class. That means if the two means are far away, this scatter should be large. That's what we aim for. So this is characterized with the help of the difference in the means. What is within class? Which is simply the scatter of the individual classes, and each individual class has what? The scatter. How do you compute it? It is just the covariance. That's all. And how do you define covariance? So yeah, it is mu I, and these are x. Okay. So this capital Xi denotes all the points belonging to the ith class. That's all. Yeah. Xi, all the data points in ith class. Okay. And mu I is class mean. So do you understand the whole idea out here? So of course now you can just place the values out here and compute within class and between class variance. I won't do the computations here, but I hope you get the clear idea of what this linear discriminant analysis does.
Yes, sir.
So yeah, once you have this covariances of each of the classes, you can just get the within class scatter and between class scatter, and then you're done for this question. Okay, so
Sir,
we'll
it
move.
was this is because S1 plus S2 because we have only two classes like X1 and X2,
Yeah,
right, sir?
yeah, yeah. So if you have multiple classes,
Oh,
then yeah, this can be extended to multiple classes, but it's not so straightforward out here. I mean, at least we are not dealing out here because here between class variance, the formula will differ. It won't be as straightforward as this. Okay, so since we are doing some sort of linear discrimination analysis, so do you understand why is it linear? Why is Fisher linear discriminant linear?
classes are linearly separable.
Uh, okay. Anything more? Yeah, if classes are not linearly separable, of course you cannot use it. That's fine. But anything more? What is this? This is a linear space, right? The LDA direction that we get. It's a linear
Yes, sir.
space. It's a one-dimensional space. It's a linear space. So that's why we are doing some linear discrimination analysis. You can also do non-linear analysis, like you have some weird space like this, uh, which can actually even increase the within class and between class scatter matrix. But then these relations will not be so straightforward out there. And generally, you tend to do this such kind of non-linear discrimination analysis using what? Using neural nets, right? Because for instance, neural nets, if you want to use it for classification of objects, objects may not be that straightforward to be classified linearly. So you might want to use neural nets instead of uh, an LD. Okay, that's just a simple use case, but we should focus on the question now. So which of the following are true regarding LDA? Okay, the discriminatory information is always the mean of the data. Is it right? Yes, no. We discussed the whole idea of it. We derived two matrices out there. So one of the
Yes,
methods is to
sir.
calculate
Mean, yeah,
mean. Yes. So it is mean of
true.
the data is useful, but is it always useful? No, it's not always useful. You also need to consider the scatter of the individual classes, right? So this part is wrong. So it is mean plus scatter of classes as well. Do you get the idea?
Yes, sir.
Okay. The next, I mean, of course, now whole of this thing depends on the data, the mean and the scatter of the classes. So ultimately, it depends on the data, which is fine. Okay. So the next thing is, it is a non-parametric method since it does not assume any distribution. What do you say? Is it right or wrong? What are the things that we compute for this method?
Mean and the scatter
Yeah, scatter is a sort of variance computation, right?
variance. Yes, sir.
So, do you think it does not assume any distribution? So, whenever you compute mean and variance, there is an implicit assumption that they are Gaussian distributed. The data is Gaussian distributed. Always remember that. So, it is non parametric? No, it is parametric since we are using mean and variance. And it does not assume any distribution? No, it implicitly assumes unimodel distribution. Unimodel in the sense for each class, there is a single Gaussian out there, which defines our mean of that specific class and the covariance of the specific class, right? So this part is true and this part is false. B is false and D is true. And the next one is it fails when the discriminatory information is not the mean, but rather the variance of the data. Is it right? Do you need an example? What is this? Again, two classes. This and these are classes. And what is the mean of this class? Somewhere here, right?
Yes, sir.
And what is the mean of this class? It is somewhere here.
Beside the triangle. Yes, sir.
Yeah. So what can you say about this? The mean is well separated, right?
Yes, sir. Mean is separated.
Mean is well separated. But what about variance?
Not separate. Not good.
Yeah. So if you consider the variance of this class, I mean these are the limits of this class and these are the limits of this class. So there is a nice overlap out here, which means that if you consider at least this specific direction out here, uh, the direction given in with this vector, yellow vector, of course this is not well separated and it surely depends on the variance. So if variance is the deciding factor instead of the mean, then it the whole linear discriminant analysis can fail. So I hope it's clear that this point is correct.
Yes, sir. Clear.
Yeah. Of course, now if you take any other specific direction for this kind of data, even then I think you cannot get a best direction where you can separate these two classes. Okay, so I hope this question is clear. Uh, okay, we did a lot of questions based on dimensionality reduction, of course, with two different types of data. One is without having labels, and one with labels. So we would like to just go to some other kind of question, which is the sparse representation. So I hope the basic idea of sparse representation is clear, that given a vector probably of size k, capital K, you might want to have only small k number of elements to be filled, which is much smaller than the size capital K. So that's how the sparse representation comes. And generally, this is obtained by having multiple bases in your matrix, which is technically termed as dictionary. So based on this, we have a question that what is KSVD, by the way? Of course, the answer is here, but I want to know what's here. What's KSVD? Where do you want to use KSVD? KSVD is a dictionary learning algorithm, right? So that's the main idea. The matrix that I was talking about. So you need to construct that matrix, and then you would like to use that matrix to project the data uh, into some other dimension where our representation of the data is pretty sparse. Okay, so yes, it's a dictionary learning algorithm for sparse representations. So that's the definition. What about this? It is a generalization of k-means clustering algorithm. Yes, no. So what does k-means clustering do?
Maybe in dictionaries we
K-means clustering. So if you know that there are k different classes that you want to divide the whole data, then you just try to find the best k, the centroids of those k data, the centroids of those k classes, such that it represents your given data best, right?
yes sir.
Yeah. So it's like you're assigning each of the data vector onto one of the class. So it is like a one hot vector where one of the element is one and all other elements are zero. So that's an extremely sparse representation of the data. So here it's like we would not like to represent it as one hot vector, but we would like to have more number of elements uh, which are non-zero. But of course, it is still sparse in the sense that most of the elements are still zero and some of the elements are non-zero. So yeah, it's a generalization of k-means clustering algorithm. And yeah, there was, I guess, yeah, in the class there was a good comparison of the k-means clustering algorithm and the KSVD algorithm. Yeah. So they try to give an idea of how k-means clustering algorithm can be thought of as a KSVD algorithm, but for an extremely sparse case. Okay. The next part is it works on iteratively updating the current dictionary until convergence. Yes, no. Yeah, it's an iterative procedure, and it updates the dictionary, that means the columns of the matrix until convergence. Convergence here means that you are not getting any further sparse vectors out there. So that's how convergence is defined. So it computes k singular values of the covariance matrix of the data. Is it right? Well, no, it's not right. Yeah, it does perform SVD k times in each iteration, but it doesn't mean that it computes k singular values. It only computes one single value out there, but with multiple matrices defined in the specific iteration. Okay, yeah. So to answer this question, this KSVD algorithm should be very clear out there. I hope uh, you have an idea of what KSVD is given the lectures. Any further doubts based on today's session?
Sir, I had a doubt about the PCA.
Okay, yeah.
Sir, like if we want to uh, use an image compression, can we use PCA to compress the images?
What do you think?
Like I had implemented, but after using the sklearn library, like I tried to implement the compression and then tried inverse transform and then got the image back. But I wasn't able to understand how was that working.
Okay, so what do you do in PCA? You're trying to find principal components, right? So,
Hello, sir. Am I audible?
yeah, yeah, yeah. I am audible.
Yes, sir. Yes,
Yeah,
sir.
yeah, yeah. So, yeah, so you applied it to compress the image, right?
Yes,
So,
sir.
given a set of images, you would have computed the principal components. So, what does those
No, sir.
principal
Only one for one image. I took the RGB channel and then compressed it into the pixels.
Okay, that's not how you do principal component analysis. Actually,
Okay.
one image
Okay.
is one data point out there. It is like a one
Okay,
single
sir.
vector.
Okay, sir. So I
So,
assumed it wrong.
yeah, I mean that's not what it's intended for. So, for instance, one of the examples given in the class is if you have multiple faces of human, assume that all the images are of
Yes,
same
sir.
size. So, what you do PCA over the whole
Yes,
set
sir.
of image data. I mean, the face image data, and then each of those images can be represented as some components along these principal directions, right? so
Okay, sir.
so
Yes, sir. Yes, sir.
if you know the principal directions, then those values of the components will be very small, right? So for if
Yes, sir.
those values of the components is very small, then you can store them in very less number of bits, so you can think of it as a compression.
Oh, okay, sir. So I saw this compression thing and like I got confused and I built it and it was like literally compressing the image size, but I wasn't able to understand why.
Okay, okay,
Sir, and I have another like last week we saw this neural network, right, sir? So I thought of implementing neural network from scratch. So I decided
okay,
to implement a square function, like y equals to x square function, like when I pass one single input, like 2, and then the output should be 4. So I
okay,
thought of implementing it with a two hidden layers. Is that possible? Because I literally spent 3 days figuring it out, but I wasn't able to train the neural network.
okay. How many data points are there?
Like I took only 5 to 10 points.
No, it won't be sufficient.
It okay, but
So
is it possible with only two hidden layers? That's what I'm asking.
two hidden layers. Okay,
Like two
you
hidden
have
layers
to.
with the two neurons.
How many total parameters out there?
Uh, 16.
Okay. So if you are using 16 parameters, you might want to use 16 data points. Okay. Um, well,
But today
it's
I figured out that like since we have to like approximate the weight as the same as x, so I thought it was like I figured that like I thought it would be not possible. I guess if we should need to use more number of layers and more number of neurons. But I like I got doubt and then I used to like I tried to implement the y equals to 5x function. Then it was able to train like with only one neuron it was able to train. So I'm thinking like, is it like if it is possible, then I'll try my best to do it. So I have doubt. That's all.
okay. Well, if first try with 100 or 200 data points. Data points in the sense that
Okay, sir.
corresponding x and y. For x equals y
Yes, sir.
equals to x square. If it works, then you can try reducing the data points. I mean,
Okay, sir. Or else I think I am like I've coded some like derivatives wrong. I felt like that. That's the
oh, you are
problem, I
coding
guess.
the derivatives by yourself.
Yes, sir.
Okay, okay.
Because I
Then
wanted to know how it works internally.
okay,
So that's
okay, yeah,
that.
that's
That's
great.
what. If that is yeah.
Okay, okay. Then maybe you should just try checking the code part as well. But okay, just for a sanity check, you can just use the existing libraries like PyTorch and code a simple
Yes, sir.
stuff. If it works there, then you can be sure that your code might
Full
be good.
error.
Yeah.
Yeah. Yes, sir.
Okay. So yep, I'll stop the recording for the session.